Download this code from codegive.com, link in the description below. OK, let's dive deep into logistic regression, covering log odds, maximum likelihood estimation, MLE, and providing a comprehensive example with code. Introduction to logistic regression. Logistic regression, despite its name, is a classification algorithm, not a regression algorithm. It's used to predict the probability of a binary outcome, 0 or 1, true or false, yes or no. It's widely used in various fields like medical diagnosis, predicting the probability of a disease based on symptoms and test results. Spam detection, identifying whether an email is spam or not. Credit risk assessment, predicting the probability of a customer defaulting on a loan. Marketing, predicting whether a customer will click on an ad or make a purchase. Why not linear regression? You might wonder, why can't we just use linear regression for a binary outcome? Here's why. 1. Linear regression predicts continuous values. Linear regression outputs values that can range from -infinity to +infinity. We need probabilities, which are bounded between 0 and 1. 2. Violation of assumptions. Linear regression assumes a linear relationship between the independent and dependent variables and normally distributed errors. With a binary outcome, these assumptions are often violated. 3. Unbounded predictions. Linear regression can produce predictions outside the 0 to 1 probability range, which are meaningless. The logistic regression solution, the sigmoid function. Logistic regression uses a sigmoid function, also called the logistic function, to squash the output of a linear equation into the range of 0 and 1. The sigmoid function is defined as where sigma, z, is the sigmoid function, representing the predicted probability. Z is the linear combination of the input features and their corresponding weights, coefficients, also known as the log odds. E is Euler's number, approximately 2.71828. 2. Log odds, logit. Before we get to the heart of logistic regression, understanding log odds is crucial. Odds. The odds of an event occurring are the ratio of the probability of the event occurring to the probability of the event not occurring. For example, if the probability of winning a game is 0.7, the odds of winning are 0.7/1 to 0.7, equals 0.7/0.3 equals 2.33. This means you are 2.33 times more likely to win than to lose. Log odds, logit. The log odds is the natural logarithm, base e, of the odds. The log odds transformation makes the relationship between the probability and the features linear. This is essential for using linear models like linear regression in the context of classification. Why use log odds? One-linearity. Log odds create a linear relationship between the input features and the output. This allows us to use a linear model, like the weighted sum of features, to predict the log odds. 2. Symmetry. The log odds are symmetric around 0. A log odds of 0 corresponds to a probability of 0.5. Positive log odds indicate a probability greater than 0.5, and negative log odds indicate a probability less than 0.5. 3. Unbounded range. Log odds can range from -infinity to +infinity. This is crucial because it avoids the probability constraints, 0 to 1, that would limit a linear model's ability to represent the data effectively. The logistic regression equation. The core equation of logistic regression combines the linear model with the sigmoid function. Where p, y equals 1x, is the probability of the outcome being 1, example probability of spam, given the input features x. Sigma, z, is the sigmoid function. Asterisk z is the linear combination of features, beta is the intercept, bias, and beta, beta 2, beta are the coefficients for the features x, x2, x3. Maximum likelihood estimation, MLE. The goal of logistic regression is to find the optimal values for the coefficients beta, beta, beta that best fit the data. Maximum likelihood estimation, MLE, is the method used to estimate these coefficients. The idea behind MLE. MLE is a statistical method for estimating the parameters of a probability distribution, in this case, the logistic regression model, given a set of observed data. The basic idea is to find the parameter values that maximize the likelihood of observing the given data. In other words, we want to find the coefficients that make the observed data most probable under the logistic model. Likelihood function. The likelihood function measures how well the model fits the observed data for a given set of parameters. For logistic regression, the likelihood function is based on the Bernoulli distribution, since each observation is either 0 or 1. Let's say we have n independent data points, x, y, x2, y2, x, y, where x is a vector of features and y is the corresponding binary outcome, 0 or 1. The likelihood function is where asterisk pi denotes the product over all n data points. Asterisk p, y equals 1x, is the predicted probability of y being 1 given x using the logistic regression model, the sigmoid function. Asterisk y is the actual observed value, 0 or 1. Log likelihood function. Instead of directly maximizing the likelihood function, it's often easier to maximize the log likelihood function, which is the natural logarithm of the likelihood function. Maximizing the log likelihood is equivalent to maximizing the likelihood because the logarithm is a monotonically increasing function. The log likelihood function is where asterisk sigma denotes the sum over all n data points. Maximizing the log likelihood. To find the optimal coefficients beta, we need to find the values that maximize the log likelihood function. This is typically done using iterative optimization algorithms like asterisk gradient descent asterisk a first-order iterative optimization algorithm for finding the minimum of a function. In this case, we want to maximize the log likelihood, so we use gradient descent. Asterisk Newton-Raphson asterisk a second-order iterative optimization algorithm that often converges faster than gradient descent. Asterisk BFGS, Broyden, Fletcher, Goldfarb, Shanoa quasi-Newton method. It is a popular algorithm for nonlinear optimization. These algorithms start with an initial guess for the coefficients and iteratively update them until they converge to the values that maximize the log likelihood. 4. Code example, Python with NumPy and scikit-learn. Explanation asterisk. 1 Data generation asterisk we create a synthetic dataset with 2 features and a binary outcome. You would replace this with your actual data. Noise has been added so that the model is not perfect. 2 Data pre-processing asterisk. Asterisk train test split asterisk we split the data into training and testing sets. Asterisk feature scaling asterisk we use standard scaler to standardize the features, 0 mean, unit variance. This is crucial for gradient descent to converge efficiently. 3 Logistic regression class asterisk. Asterisk underscore underscore init underscore underscore, initializes the learning rate, number of iterations, weights, and bias. Asterisk underscore sigmoid, implements the sigmoid function. Asterisk fit, implements gradient descent to update the weights and bias based on the training data. The core of the algorithm is in the gradient calculation and parameter update steps. It also prints the cost every 100 iterations to monitor the progress of the training. *predict predicts the class labels, 0 or 1, for new data based on the trained weights and bias. It returns probabilities. *predict_proba predict the probability of each class. For training and evaluation *. We create an instance of our logistic regression class. *. We train the model using the fit method. *. We predict on the test set using the predict method. *. We evaluate the model using accuracy_score and confusion_matrix. 5. Visualization, optional. We create a function to plot the decision boundary of the logistic regression model, which is helpful for visualizing how the model separates the classes. 6. Comparison with scikit-learn, optional. We compare our implementation with scikit-learn's logistic regression class to verify that our implementation is working correctly. Key points to note: learning rate. The learning rate is a crucial hyperparameter that controls the step size in gradient descent. A smaller learning rate might take longer to converge, but a larger learning rate might overshoot the optimal values. Experiment with different learning rates to find the best one for your data. Number of iterations. The number of iterations determines how many times the gradient descent algorithm will update the weights and bias. Increase the number of iterations if the model hasn't converged yet, the cost is still decreasing. Regularization. Logistic regression can be prone to overfitting, especially with high-dimensional data. Regularization techniques, L1 or L2 regularization, can help prevent overfitting. You can add regularization terms to the cost function and modify the gradient updates accordingly. Scikit-learn's logistic regression class has built-in regularization options. Optimization algorithms. You can experiment with different optimization algorithms like Newton-Raphson or BFGS to see if they converge faster than gradient descent for your data. Libraries like SciPy provide implementations of these algorithms. Multi-class logistic regression. This example focuses on binary classification. For multi-class classification, you can use techniques like 1vs rest, over, or multinomial logistic regression, softmax regression. This tutorial provides a solid foundation for understanding logistic regression, log odds, maximum likelihood estimation, and how to implement it from scratch. Remember to adapt the code and concepts to your specific data and problem. Good luck.